So here's some definitions. These are in chapter 2 of your book. Kinematic chain is an assemblage or collection of links, and I'll define a link more rigidly in a moment. And these links are connected by joints. I'll also define those in detail in a moment. And they're connected in a way so as to provide some predictable kind of motion. And this, again, is a silly example of that. So each of the sides of this chair, if I just take the arm and the legs over there in two space, that's a kinematic chain. And I can walk around the room with it under my arm. A mechanism is defined as a kinematic chain in which I've taken one of the links and fastened it to something. So if I take this and sit it on the table, I can still articulate it, keeping the thing on the table, right? Now, by definition, that's become a mechanism because I've tied one thing down. Let's say I've tied that down. It's a subtle distinction, and not a horribly important one, but something you need to understand. So a kinematic chain is free to be moved about the room. A mechanism has been screwed down to something. It's the same kinematic chain, but I took out my drill and I screwed something down to the ground plane, the floor, the table, the wall, whatever, okay? I define a machine as opposed to a mechanism as a combination of resistant bodies arranged to compel mechanical forces of nature. That's actually not my definition. That's out of some other reference. To do work accompanied by determinate motions. It's a very fancy definition. But what's the distinction here between a mechanism and a machine? It's very fuzzy. I don't think I'd call that chair a machine. It doesn't have a motor. It doesn't make noise. It doesn't blow smoke. So I don't think it really constitutes a machine. I'd call it a mechanism, certainly. A machine implies power, large amounts of energy being transferred or controlled in some fashion. So it's a very fuzzy distinction between machine and mechanism, and the terms are often used interchangeably. But to be fussy, and we have to try to be fussy when we introduce a new topic, they are used differently to mean slightly different things. And all of the above examples contain links and joints, which we'll now define in somewhat more detail. For our purposes in kinematics, we're going to assume that everything is rigid, that we cannot deflect them because we're ignoring forces. And that's one of the handy benefits of dividing dynamics into two pieces, kinematics and kinetics. Kinetics, we have to worry about the other stuff too. So we're assuming that they don't have any elasticity, which is another way of saying that these holes in my link, which I refer to as nodes, can't move toward or away from one another, right? So once I drill those two holes in the link, my assumption is those holes will never get closer together or further apart. Because in reality, if I put enough force on that, I can stretch it, right? But we're ignoring forces. So we can talk about links having different flavors, like a binary, ternary, quaternary, and those are just fancy terms for the number of holes. And it doesn't say a thing about the shape. I've drawn them with nice regular shapes. But this could be shaped like a pretzel and have 4 holes, and it's still a quaternary link. It's the number of holes that determine what it is, right? Shape, it doesn't matter. So 2 holes, 3 holes, 4 holes, 5 holes, 6 holes, whatever you want. In reality, I can make most mechanisms out of those 3 flavor links. So the key here is they're rigid, and the holes determine the order of the link. So the order is the number of nodes or holes. The joints are more complex and a lot more numerous. Now the joints allow a degree of freedom to exist between the links. The simplest example is a pin in a hole. 2 links, 2 holes, put a pin through the 2 holes. You now have an assembly, a kinematic chain, also called a dyad because that means 2. So I got 2 links connected together. It's a dyad. That's what this is. This is a dyad right here. So we call this a first order pin joint because we have a pin connecting the 2 links. This is a second order pin joint because I have 3 links and 2 pins. And the order refers to the degree of freedom. So in respect to the way I can move the pink link versus the gray link, I only have 1 degree of freedom, delta theta, rotation, right? So imagine you grab the pink link in one hand, you grab the gray link in the other, and you're going to move the gray link. You're not moving your pink one. You move the gray one, it can only rotate. So that's 1 degree of freedom. So that joint allows 1 degree of freedom. First order joint. That's also in the top left corner. The top right corner shows a translating analog of that pin joint. So instead of having a pin in a hole, I've now got a block in a slot. And I can move the pink block left and right through a delta X, and that's 1 degree of freedom. So we refer to these 1 degree of freedom joints as full joints. They're the real deal. It's a complete joint. It's got 1 degree of freedom. On the one row down on the left of the panel, I show some kind of a stick sitting on a plane. And again, we're still thinking 2D here, so I'm not going to allow that to move out of plane. So there's my stick, and the table's the plane. So I can move that stick back and forth on the table without rotating it, or I can hold it in one spot and rotate it. So it has about a point. So it has 2 degrees of freedom potential between this stick and the table when I put them in contact in that fashion. So we call that a 2 degree of freedom joint, but it gets the name half joint because the 2 ends up in the denominator. So it's referred to as a half joint because it has the effect of half as much as the 1 degree of freedom joint, as you'll see. So there's 2 flavors of joints, full and half, depending upon how they constrain the 2 things joined. I have no joint at all. This is a link. There's no joint until I marry it to something else. They have to be 2 things. It takes 2 to tango. 2 things together constitute a joint of some sort. Okay? What else have we got here? Pin and slot. That has the same kinematic characteristic as this link on the tabletop, except that I now can't pull them apart. So the one I have in my hand, the link sliding on the tabletop, which I can also rotate, thus it's 2 degrees of freedom, I refer to that as a force-closed joint. I have to push down on it to keep it together. Once it comes apart, the joint disappears. It doesn't exist anymore. Okay? So I have to have a force, which could be gravity or it could be a spring or something on my hand, holding it together to make the joint exist. If I put a pin in a slot, I now call that form closed by the geometry, because the pin is trapped in the slot, and thus I don't have to have a force to keep them together any longer, but I still have the 2 freedoms, because I can move that pin left and right along the slot, also rotate it about any point. So kinematically they're the same, but their constraint is different, and in one case I have to put a force on it, in the other case I don't. This is a unique kind of joint. It's a wheel on a surface. And this is sort of schizophrenic. It doesn't know what to be. It could be a full joint, provided that I don't allow the wheel to slip. Imagine it's your bicycle tire or your car tire, both of which are made of rubber, which has a high coefficient of friction. And you're typically riding on a surface made of macadam, or concrete, which also has a high coefficient of friction. And so as I pedal my bicycle, I don't tend to slip the wheel, and I have 1 degree of freedom between the 2. So the wheel rolls on the surface, and the degree of freedom is the theta of the wheel. Wheel's turning. Huh? Make sense? Now suppose it's wintertime, which it will soon be, and there's ice on the ground. Now, especially if I try to stop, this thing's going to slip, and I have a 2nd degree of freedom potential, which is not rolling but sliding. So this has the potential for 2 freedoms. Whether it exhibits the 2 freedoms or not depends upon the friction characteristics between the 2. Make sense? So this is somewhat unpredictable as to how it will behave. Depends on external conditions. I show some other sketches on the left panel here. A screw thread in a nut is a 1 degree of freedom joint. The input is delta theta. I turn the screw. It advances in one direction. So I have one output for one input. That's a full joint. A cylindric joint, this is a round pin in a hole, cross-section thereof. That has two freedoms because I can both rotate it and slide it. If I want to get rid of the second freedom, I've got to put some constraints on the z direction so it doesn't move, or x, whichever you want to call it. So I can't move it left to right, but it only rotates. This is now called a revolute joint, and that's 1 degree of freedom. This spherical joint, or joystick, has 3 freedoms, all of which are angular. And the planar has 3 DOF. That's my book on the table. And I can move it in X, Y, or rotate.